back to the Cerberus saga, everyone. We have had more stress tests of Cerberus, now stress test running on the Z80 CPU. Last time it was only on the 6502. And more fine-tuning of the architecture, well, not the architecture, but the detailed hardware specifications of Spacer, the system controller here in the center, and of the BIOS code, the input-output, basic input-output system here in the onboard flash memory of CAT. I'm going to discuss all that today, but there is one thing I mentioned last time. I needed a bodge here because I needed to connect the weight input of the Z80 to Spacer, and Spacer had an unused connection to the refresh output of the Z80, which is completely useless. It was, I think, in this pin here. So underneath the chip, inside the socket, I needed to cut a trace. And then I needed to apply a bodge directly to the pin. I bent out a little bit this pin in here. It's ugly, you see. And the reason I did that is that when I designed this board, for some reason I didn't expect to use the weight input of the Z80. And then of course you have to pull it up. You have to connect that to VCC. You cannot leave an unused input floating. It's very bad PCB design if you do that. So if I would put this pin into the socket, it would just be pulled up and I wouldn't be able to use it. So now there is this little bodge. It wraps around and it goes here on what was the pin connected to the refresh of the Z80, and now it's connected to the weight input via this bodge. It's ugly, it's horrible. I don't like it. I don't even like to see it, but I needed to show it to you. So there it is. Put it all back and turn it on for you to see what's going on. Okay, let's turn it on now. You've seen this before. I'll give you a general tour of everything that is new. Yeah, the screen was not in focus on the camera I was using, so let me show you how it actually looks like. The starting screen is this. I'll take a minute with this other camera, just show you some functions like help, which summarizes the commands available from the BIOS. That's a directory listing. All the files on the micro SD card are listed in there. There's a test memory function that writes the character set and reads it from each of the 4 memories, so that's what you see there. Now I'm switching mode to the Z80 CPU. I'm going for fast or 8 MHz clock. And then I'm loading a little application called cellz80.bin. That's a cellular automata, a Rule 30 cellular automata. It runs very fast on the Z80, as you will see now. So if I press S, I can stop and step it, so you see the image that is actually being generated. And if I let it go, it runs very fast again, as you're about to see. And when I quit the application by pressing ESC, the standard character definitions are reloaded, so the white brick will become that what you see there, that gray brick, and we return to the normal BIOS prompt. I can list memory from address 202, which is the beginning of the code area. So that's basically it in good images. That's what it looks like. I will go back to giving an overview now with the other camera. I have managed, thanks to a very valuable hint from one of my viewers. I will be putting his name underneath the screen right now. Thank you very much. He has given me a hint about how to instruct the compiler for the ATmega 328 code to put all the strings, the character strings in the code, in code memory as opposed to dynamic memory. And dynamic memory was my bottleneck. And by doing that, I saved a lot of space in the flash memory here of CAT. And I was able to put back a lot of the functions that I had to remove and add some comfort functionality, even useful functionality that I wanted to add and I couldn't before because I thought I was running out of dynamic memory. So to give you an idea, for instance, I have now this help command, which gives you a short screen with all the commands available. The 0x command that allows you to enter bytes directly into memory, whole lists of them. The list lists the contents of memory, the clear screen, test memory, 6502 mode, Z80 mode, fast and slow to change the CPU clock speed, reset, which resets the entire system, I'll show you in a second, the directory, delete, load, save, run code in memory, and I added this block move. It moves the contents of memory in between addresses 1 and 2, which you put in the command line, to address 3 onwards. So it allows you to make huge block moves with one command from one position in memory to another, very helpful. And of course this help command and the ask to quit CPU mode. And the little functionality I had before, if you press the up arrow key, the previously typed command returns. So that functionality is back as well. I'm very happy with that. I have more test code now. So now I have the cellular automata application for the Z80. It's a tiny file if you compare that to the same application here for the 6502. It's 282 bytes, and for the Z80 it's 207. The Z80 has much more powerful instructions, allows you to code the same functionality with a lot less bytes, as you see there. So we can now do a stress test on the Z80. So for that, the first thing we have to do is to go from 6502 mode to Z80 mode. That's what we do here. So now we are Z80. It's running at 4 megahertz. Let's get ambitious and go for fast. So now it's Z80 at 8 megahertz. So now we are going to load this application, cell Z80.binary. And if everything is okay, it will add these 207 bytes here to the beginning of the code area, which is address 202 in X. So this is the application, and from this point onwards as well, of course. So it is in there. So now I will run, and I will immediately press S to step it, because I want you to be able to see something. So there you go. It's the same cellular automaton application. The Wolfram's Rule 30 cellular automaton. The same you've seen before. I can just press S to step it through. If I press any other letter, it will run automatically. But it's an interesting application because it forces Cerberus to software scroll the screen up every time it adds a character line to the bottom. It has also changed the definition of one character. The character token being used here is that checkerboard character, grayish, and I'm using that and redefining it into a completely white brick, and just to test that the Z80 is also changing the character definitions here. Of course, I have a default character that is a white brick. I'm not using it on purpose in order to see that I can change the character definitions there, and I am. The application has just done that. If I quit the application by pressing ask, the original character definitions will be reloaded from the micro SD card, and the screen will be built up with that checkerboard character. You see, if I press ask, pay attention, see, it changes it to the original character definition. But if I run again and I let it fill the screen again, there you go. Now the nice thing about this application is that it's complex enough to really stress test the buses and the control performed by Spacer, which is what characterizes Cerberus. It's what makes Cerberus Cerberus. But I'm familiar enough with it that if you just show me one arbitrary screen produced by this application, I know if it is correct or not, because I'm used to the patterns that are generated. And why I'm saying this is because to stress test, I cannot step through it. I have to let the Z80 go on its own speed, and then you don't see anything. Look, I will let it go on its own. Maybe occasionally you see a triangle going up, but it's impossible to discern, especially with this camera I'm using now. It's capturing it at 30 frames per second. With a 60 frames per second camera on my mobile phone, you probably see more. I'll be overlaying this right now, my mobile phone image at 60 frames per second, but even then it's very fast. So to stop it, I just press S, and then I can, just by looking at this frame, I can see if it's correct or not, because I know the application, and I can step through it again, let it run a little bit again, stop and check the frame, let it run a little bit more, stop and check the frame, a little bit further down. So I've been doing this for quite a while as a stress test. When I started doing this earlier today, very occasionally there would be a wrong character, or the scrolling would be faulty. The line would change when moved from one position to the next. Very, very, very occasional, and sometimes it wouldn't register my pressing the S key to stop it or to step through. I would press and nothing would happen. I would have to press again. It happened 2 times, I think, and the faulty characters, I caught it twice as well in the course of the afternoon doing this, testing this. But I fixed it. I will explain later in this video what the fix was. It's just fine-tuning of the logic here in Spacer, and one thing that was necessary to make sure that I wouldn't miss a key press, I am no longer withdrawing the clock from the CPU that is selected. Before, I would withdraw the clock from both CPUs if cat was active and owning the buses. Now, when cat is active, the CPU that is selected, there's always one of the 2 CPUs selected. The one selected, say the Z80, will be getting the clock, but its buses will be tri-stated and it will be halted. But it will be getting the clock. And the non-selected CPU will not be getting the clock, and then it will go into a very low power standby state. Now, the reason I'm not withdrawing the clock anymore from the selected CPU is that withdrawing the clock from the Z80 was part of the reasons why it sometimes, or twice, it missed my pressing a key. And the reason is, unlike the 6502, which accesses the memories in one cycle, the Z80 has a 5-cycle structure to access memory, and at each of those cycles something else happens and it needs a clock. So depending on the moment in which I would press the S key, I would withdraw. That's my conjecture. I couldn't replicate the problem frequently enough to really drill down with the logic analyzer, but my conjecture was that depending on when I pressed the key, I would withdraw the clock in the middle of those 5 cycles, or the first 3 cycles, which would prevent the Z80 from actually recognizing that I pressed the key. I would withdraw a clock that I shouldn't withdraw. I should withdraw the clock a little bit later. So to prevent that, when the CPU is paused, like for instance if I press ESC, the Z80 is selected. If I press ESC, the Z80 is still selected, but now cat controls the buses. So the Z80 is now getting a clock, but it's halted and its buses are tri-stated. In other words, it doesn't interfere with the buses. The only thing I lose is, a little bit more power dissipation, but nothing minor, nothing to be worried about at all. So doing these 2 things, allowing the clock to stay with the selected CPU even when it's not running, and fine-tuning the memory management logic here in Spacer, and I will show the details to you later in this video. Doing these 2 things has smoothened out the last wrinkle in Cerberus. It's now, as far as I can see and check and measure, it's now rock solid. This stuff is running at full 8 megahertz. There are no wait states, no default wait states to access the memories, only when there is a conflict in one of the read-write memories, one of the dual-ported memories. Then there is 1 or 2 wait states added, but that happens extremely seldomly, and it will not have any performance, any measurable performance penalty. And I have let it run like this for hours on end, stopping it every now and then to see if the algorithm was going correctly, to see if there was any wrong character on the screen, and for hours nothing was wrong. So as far as I can determine without a commercial scale stress test that would run for weeks and would need several people to write code for and monitor. So short of that, Cerberus is as tested as I felt like doing that under reasonable hobby conditions. I really cannot find anything wrong with it at all, even in the worst case scenarios. It's just running fine. It just does what it's supposed to do without any error. Now, we can do this also for the 6502, of course. We can go to 6502 mode. But then this code that is in memory now, that's Z80 code. If I were to just execute it now, nothing would happen because it's not 6502 code. So we have to load, let me see, this is the fast one, fast6502.bin, 6502.bin. Now this one now has a surprise, has a special thing. I will just start it. Look, you see? It's not just a square now, it's not just a brick now. Now each time I step, the character changes. So what this code is now doing is at every cycle of the code, not only does it add a line to the bottom, a new line that needs to be computed to the bottom of the screen, and software scrolls everything one position up. In addition to that, it redefines the character being used by writing 8 bytes to the character memory every cycle. Every time you scroll one position up, 8 bytes are written to the character memory to redefine the definition of this one character being used. And it has the effect of a sort of pulsation. It pulsates. If I step slowly through it, you can see how the characters change slowly, how they become smaller each time until they get to the minimum size, which is this. Then it gets repeated, and then it begins to grow rather quickly, and then it starts decreasing again. If I just let it run, you hardly see it. You see just the pulsation, but you don't see the triangles as they scroll. But I can do the same thing. I can step through it, let it run, step through it, and this stepping through also exercises all the protocol between CAT and the CPU, in this case now the 6502, as the CPU is running. Because if I press a key on the keyboard, the signal comes from here through these lines. It is CAT that is interrupted while the CPU is running. CAT is listening to the keyboard in parallel, and then once CAT has acquired the key, it will halt the CPU, tri-state the CPU so it gets control of the buses, write the ASCII code of the key pressed here in the low memory, write the new mail flag to 1 in the low memory. Then it will let the CPU go and send a non-maskable interrupt request to the CPU saying, okay, there is something new for you. All this happens each time I press the S key. And if I do that several times and it never misses, actually it does that each time I press the space key as well. So it never misses it and nothing gets screwed up in the execution, then you also know that this synchronization and communication protocol is working just fine. Now this is too fast. Becomes basically invisible. So if you go to slow mode, so now we are at 4 megahertz, and then you can just run again because I didn't change anything in the memory. Now it's a little bit more visible. You see the pulsation a little bit better, things are more discernible. I can do the same thing. I can just step through it or let it run and it's more visible. Now one thing that to me is not unexpected, but I find remarkable, if I go back to fast and run it, granted there are 8 writes to the scan, to the character memory here to change the character definition. Those 8 writes are not done by the equivalent application on the Z80, but beyond that the applications are entirely equivalent, and just 8 writes is not much, but you get a feeling for how fast it goes up, especially if I use 60 frames per second footage to show you this. Then you can see that the triangles pass very quickly through the screen going up. But if I quickly go to Z80 mode and I load the same application for the Z80, except that I don't change the character definitions and I just run, you will notice that it's a lot faster than the 6502. And indeed, it's about twice faster than the 6502, even though the Z80 is running at 8 MHz and the 6502 as well. The Z80 is a processor that is much easier to make run at a higher clock speed. You know, in the old days, you would typically have Z80s running at 3.5 MHz and 6502s running at 1 MHz or 1.7 something megahertz in the case of the Atari 8-bit line. But the Z80 always runs faster because it's a better architecture. It runs faster. But in this case, I'm not being fair to the Z80. I'm running both processors at 8 megahertz, and the Z80 is still a lot faster. And the reason is the following. The Z80 has hardware optimized instructions for moving large blocks of data from one position in memory to another. You can actually perform an entire vertical scroll through software in the Z80 using only 4 assembly instructions. In the 6502, you need an entire routine. You need pointers in the dreadful page 0. You need to keep administration about how you increment those pointers, the low byte and the high byte. It's all kinds of things that you have to pay attention to. While in the Z80, 4 assembly instructions, hardware optimized, that's why you have this extremely fast scrolling, so fast that it makes it useless. In the case of Cerberus, coders will have to add slowdown code unless they really program a heavy application computing a lot of stuff. But for most games, programmers will have to add delaying code to prevent this from happening. It's just too fast. The Z80 is too fast. Anyway, what else can I show you about Cerberus? I think I've shown most of what is available. Let me see if... Oh, I want to demonstrate this move function. To do that, let's fill the memory with values from 0 to 255. If I do this test memory function, it will write the character set to each of the memories and read the character set from each of the memories. So it will write the character set to the low memory, then read it from the low memory and write it to the high memory, read it from the high memory and write it to the video memory, and then the video circuitry will read out both the video memory and the character memory to put out a VGA signal. So this tests the entire memory hierarchy. And in doing that, what it will do, if I just list from 0, it fills the memory positions with sequential hexadecimal numbers, as you see here. Now we can experiment with moving this entire block of code here to another area of memory. So let's see, let's go to address 2000. Let's see what is in address 2000 right now. It's random stuff. You see, there's nothing sequential here. But if I move, let me see which addresses I have to go to. If I move from 0 to B7, so let's list 2000 again. And now I move from 0 to B7 to address 2000. So all the memory contents between address 0 and B7 inclusive will be moved to the block starting at address 2000. So they will fill this screen. Let's see what will happen. It will automatically relist it. So we should have sequential numbers here if this command works. And of course it will not work because I put a more and not a move. Move 0 B7 2000. There you go. You see, you have from 0 to B7 now in address 2000, which is a copy of what we had in address 0. So that's the block move function. I find it very useful. The others I have demonstrated before. Deleting a file, loading a file I used today, saving a file I have demonstrated before, run I used today, help I used today, CLS is obvious, just clears the screen. I think adding bytes is worth to show. Suppose I want to change the contents of the first 8 bytes in memory, then I just list the address and I say I will start from address 0 and I want to put FF 8 times. If I do that, this should change to FF. because I'm just entering the bytes one by one. And I can do that with any number of bytes. I can continue here another 3 times, and these 3 positions will be filled with FF. There you go. So that's the manual entry of data into memory. You can add opcodes. So in principle, if you do this entry of bytes from address 202, you can just type the address and just put bytes and put whatever you want there. You can program the machine by entering the opcodes directly. It's a pain in the neck, but this is a full-fledged now machine code monitor. It's not an assembly monitor. It doesn't translate mnemonics to opcodes and vice versa, but it has all the basic functionality you need to do anything you want with Cerberus. It's cumbersome, but it's all there. So if I enter this command line here, these values will be entered in the code memory. There they are. So I just programmed Cerberus with nonsensical opcodes. And of course, I can reset it. And what I wanted to show you, if I list 2000, where we have the sequential numbers, if I reset Cerberus, it will reset both CPUs and CAT, but it should not touch memory. So let's do this test. Now let's just go and list 2000, and should still have the same. Yeah, there they are. They are intact. So Cerberus can be soft reset without destroying anything in memory. Alright, let's have a look at the final version of the spacer hardware description in couple. We've discussed most of this, so I will go only for the parts that have been fine-tuned in this latest round, which was the final round of stress test and fine-tuning. And most of the changes are here in the memory management logic, and there is one change here in the clock management logic that I already alluded to. Here are the 2 equations for the 2 CPU clocks, the clock 6502 and the clock for the Z80. They both are based on this raw clock, which is this equation here, which basically selects either a 4 MHz clock or an 8 MHz clock, depending on this signal, CPU speed, which comes from CAT. And then notice that there is no more CPU go in these equations here. The clock is only withdrawn if the respective CPU is not selected. So CPU selection, when it's 0, the 6502 is selected, and then this will become a 1, and with raw CPU clock, you get raw CPU clock. So the 6502 has a clock, and if CPU select is 1, then the Z80 has a clock. The clock for CAT is unchanged. Now, if we go back up to the memory management logic, here there are some changes. Previous time I was using this memory request signal from the Z80, which the Z80 asserts or activates when the address on the address bus is stable during a memory read or write. And I was using it to end with the write signal from the Z80. But if you look at the timing diagrams, it's unnecessary to end the write with the memory request, because the write is always activated within the activation period of memory request. So you're not shortening the write pulse, you're not doing anything. So we can leave the write pulse here alone in the equations for the write signals that go to the memories. But the memory request is useful in the sense that the chip enable for the 4 memories, there are 4 chip enable signals, they are based on what is on the address bus. These signals here are address bus bits. I even put a comment here to illustrate what the translation is. So address line 15 corresponds to SLRO 15, and address line 14 to this one, and so on and so forth. So depending on the address on the bus, spacer will activate one of the memories and only one of them. But of course, this is so if these address lines are stable on the bus. So the usefulness of the memory request signal is to gate the chip enable of the memories to make sure that these chip enables only go active when the address is already stable. And guess what? With CAT, we have an equivalent signal. We have the address output enable, an output of CAT. So when CAT is accessing memory, we can also use this AOE signal here in the same way that we use the memory request from the Z80. Now the 6502 has no such thing, as you probably have gathered already along this saga. I much prefer the Z80 to the 6502 in all aspects. It's easier to design hardware for it, it's easier to program it, it's a more powerful processor. But anyway, the 6502 just puts an address on the bus, so there is no way you can wait for it to be stable. So here I just put a logic that tells spacer when the 6502 is selected. But when CAT controls the bus, or when the Z80 controls the bus, we can use these two terms here to construct an internal variable called enable, which will activate only when the address is stable on the address bus. And then we end all the equations for the chip enables with this enable term at the very end. So the chip enables will only become active when the address lines on the bus are stable, except in the case of the 6502, but that's okay because we know that it works even without that. But anyway, I've added this now for extra stability of the address bus. I think for the Z80 this was an important thing to change to get robust and reliable performance. These are the write signals for the memories. So we have the read-write for the video memory, read-write for the character memory, write enable for the high memory, and write enable for the low memory. These are largely what they already were. I didn't change. But the output enable, which is common to all four memories, here we needed to change a couple of things. Let me explain to you what it is. The Z80 has separate read and write signals, and both are active low. And I'm using pull-up resistors on them. So this signal here, RD-Z80 or read Z80, will only activate, and it's active low, it will only go low if the Z80 is actually selected and running, because otherwise the pull-up resistor will just make the signal high or inactive. So we don't need any other term to make sure that when this signal is active, it's meant to be active, because it can only be active if the Z80 really forces it down, forces it into activation. But for CAT and the 6502, the story is not the same, because both CAT and the 6502 use only one bit as a read and write, instead of two different bits, like the Z80, which has the write bit and a separate read bit, both active low. For CAT, if the read-write bit of CAT is high, it means it's a read, and if it's low, it means it's a write. So what you could get in a situation like this, if you don't add this extra logic that you see me adding here, these terms, if you don't add the address output enable, for instance, the read-write bit of CAT will be in a read position, and you may activate an output enable when in fact you don't want. Because CAT may not be running the show, it may not be owning the buses. Maybe there is one of the CPUs running the buses, and CAT just has a high RW bit, because the high or read is the default value. So to prevent a misunderstanding there, I'm ending it with the address output enable of CAT. So this will only become valid if CAT is actually owning the buses and putting an address on the bus. And the same thing for the 6502. This was the term that was there before. With the 6502, you have to end the read-write bit or read-write bus with the clock to shorten the pulse, so you avoid spurious writes. But now I'm ending two other terms with it. The CPU go, which is active only when one of the CPUs controls the buses and not CAT, and the CPU selection bit to say that not only the CPU is go, it is CAT. Sorry, it is the 6502 that is go, and only under these two conditions, then if this bit here, the read-write bus, is high, then it's a real read and not just a default value for that bit, which will be high even if the 6502 isn't active or isn't selected or isn't running the buses. Now, perhaps the most important thing I've changed is this. Well, first of all, you will notice that I have simplified these equations here for the internal pause signal. They do exactly what you saw before. It's just that the logic is simpler. I'm not checking which busy condition comes from which of the dual-ported memories. If one of the dual-ported memories is issuing a busy and it's cat trying to write, then we pause cat. And the reason is, if there is a busy signal and cat is trying to write, then it can only be cat writing. The other CPUs will be inactive by definition if this signal here, read-write cat, is in a write position. So we don't need the more involved, didactical but more involved logic I had before. Same thing applies here. If one of the busy signals from one of the dual-ported memories is active and it's the 6502 trying to write, not only accessing memory but trying to write, then we know that the busy signal is applicable to the 6502, and then we have to pause the 6502. So these two things are equivalent to what you've seen before, just simplified, but now there is something else going on here. And the reason is, if I would follow the pattern you saw in these two and just to use the write Z80 signal, or this signal here, to determine the pause signal, if one of the dual-ported memories is busy and it's the Z80 trying to write, then we should pause the Z80. If I just use this signal, it doesn't work. And the reason is, this signal here comes pretty late in the memory access scheme of the Z80. First, the memory request signal goes low, and only much later the write signal goes low, which means that the busy signal will have been active already, because the comparators in the dual-ported memories will kick in as soon as the address is on the bus, and that will happen even before the memory request signal goes active. So the write signal comes too late, and I think that was not working. So I've replaced it. I've replaced it for the memory request when that one goes active, but that one goes active whether it's a read or a write. So how do I identify a write if I cannot use the actual write signal because it comes too late? Well, it turns out that if I end these two signals, when memory request goes active and the read is not active because it's active low and I'm not inverting it, so the read is not active means it's not a read and there is a memory request. Now we know it is a write. And this works because the read pulse in the timing diagram of the Z80, you can see that it's a longer pulse that will be inactive throughout the memory request signal activity. So this will be equivalent to a write signal as long as the memory request, which goes active as soon as the address bus is stable. And that will catch the busy signal soon enough in time to avoid a miswrite in memory. This works. Now, on the BIOS code running on the little Atmega 328, the thing that saved me was the use of this F macro. If you put this macro around all string constants in your code, the compiler will put these constants in the instruction memory, in the flash, instead of the miserable 2 kilobytes of dynamic memory that were being used up with these constants. There is no need to put a string constant in the dynamic memory. So by using this F macro, telling the compiler to do this everywhere I could, I saved a lot of memory, which allowed me to do more things and to build a proper BIOS, a basic input-output system into Cerberus from the get-go. So this is also the final version of the BIOS, or final version for the first release at least. We will just scroll through it very quickly just to get a sense for it. This stuff is compiled from within the Arduino IDE using an Arduino Uno as target board. but that will be the result will be fine to upload into a standalone Atmega 328P, which is what we have in the Cerberus board. Now this is that extra array to store the contents of the command you just typed before in the edit line, so you can recover it by typing up arrow. So these are the 38 bytes that I put back because now I had the space for them. These are just pin declarations, default value for the pins. The code starts by resetting the CPUs. There is a function reset CPUs down that I will show you in a bit. It initializes the SD card or the micro SD card where the file system is. Then the next thing it does, this part of the code will immediately upon startup load the character definitions, which is a file in the micro SD card, which has to be in that micro SD card when you turn on Cerberus, the chardefs.bin. Instead of calling, there is a reason I'm not calling the load function from here, and that's probably a bug in the Arduino IDE, so I'm just copying it here. If I just call that function load, sometimes the system loses track of which files are open or closed, and you end up not being able to close or open a new file. So to avoid that, I just repeated it here. Then it clears the screen, prints the wireframe that you saw. It opens another file, CerberusIcon.img, which is that three-headed dog you see when Cerberus starts up. For the same reason as before, there is direct code here to open the file. Prints the status, plays that little jingle, and gives you the edit line. Now within the loop, we are basically checking which keys the user has pressed. I only highlighted the important ones. If the user has pressed the ESC key and the CPU is running, then we have to stop the CPU. And to do that, we will pull the reset pin of cat high, so spacer resets the CPUs. We will stop the CPU by setting CPU go low, giving it a little bit of time, and then finishing the reset cycle. Then we will automatically reload the standard character definitions, because the application the user was running on the CPUs might have changed the character definitions, and we don't want to inherit those changes in the BIOS, otherwise you don't know what you're going to put on the screen. So those are re-uploaded, and then we just reformat the screen. Now, down here, that's what happens by default when the user presses a key. If the CPU is not running, then you just capture the key the user presses, because it's going to be a BIOS command line input. But if the CPU is running, then that key press is supposed to be recognized by the application running on the CPU. So cat has to pass it to the CPU. And the way to do that is to first stop the CPU, halt the CPU by pulling the CPU go line low. Then it will put the ASCII code of the key that has been pressed in the mailbox at address 201. And then it will put 1 in the mail flag, which is address 200, so the CPU knows that whatever ASCII code is in address 201, it's a new, recently pressed key. Then it lets the CPU go and immediately issues an interrupt to the CPU in case the CPU is waiting for an interrupt, is waiting for a keyboard input, like some text editors. Unless you type on a key, the editor does nothing. It's just sitting there waiting for the interrupt. So the BIOS has to issue that interrupt. This is just the part that recognizes whatever the user typed on the command line or the edit line, whether it was list, whether it was test memory, clear screen, and so on and so forth. We've seen this before. I will skip it. This is a very simple parser, so we can recognize what the user typed in the edit line. This is the help function, all with this macro F. So all this text here goes into the instruction memory, which we have enough. I can show that to you. If I click on this to compile, the compiler will tell us how much memory is available. These warnings are for one of the libraries, the PS2 library. It has nothing to do with Cerberus itself. So you see, we are using 78% of the instruction memory and only 52% of the dynamic memory, so this opened a lot of space. Now this is the binary move function to move the contents of memory, blocks of memory from one location to another. You just saw a demonstration of this today. I'm not going to all these details. The core of the function is very simple. It's one for loop in which we pick a certain value from a memory position and then poke it into a destination and then increase the destination. That's all there is to it. Everything else is just to check that the user has entered all the arguments that are needed, all the file names or addresses that are needed in issuing error messages if that's not the case. That's the list function. Again, the core of the function after you check for potential errors or missing arguments, whatever, is just a loop in which a string is printed containing the values that are picked from memory. So you're just listing the content of memory. Now this is a function I want to spend a little bit more time on. Programmers for Cerberus need to know what happened when the user types run. When the user types run, it's this function that's executed, run code. And the first thing it does, it clears the entire screen. So this is a Cerberus clear screen, not a normal clear screen, meaning that it will erase the frame as well, that wireframe that you get with the BIOS code. Then it will clear the mailbox and the mail flag, just in case there was rubbish there. We have to start clear, so those two positions are reset. And then it checks the mode. In one case, it's the 6502 that's supposed to run the application, and in the other case, it's the Z80. So if it is the 6502, the first thing we need to do is to make sure that the non-maskable interrupt vector points to address FCB0, which is the first address after the video area. And that's just a convention in Cerberus. I had space there, so I decided to put the interrupt vector pointing there. And now if the vector is pointing there, we need to fill it in. We need to put an interrupt service routine in there, which in the case of Cerberus, by default consists of only one instruction, return from interrupt. Because for the rest, the CPU application can just poll the mailbox and the mail flag. If you are, as a programmer, really want a true interrupt service routine, so polling is not needed, then you have to go and change the BIOS code of Cerberus, which is trivial. It's like writing an Arduino sketch and uploading it into CAT. There is a port on the board to allow you to do that with a traditional FTDI adapter that costs, I don't know, $3. So you can do that, but by default, the interrupt service routine is just returned from interrupt, and the CPU has to poll the mailbox and the mail flag. Next thing we do is we fill in let me see. Now this is the interrupt service routine. The opcode 40 is just the return from interrupt, and then we fill in the reset vector. The 6502 will go to these two addresses, FFFC and FFFD, to get the address of the first instruction to be executed. And as we've seen in Cerberus, by convention, that address is 202 in X. So we need to put 202 in that reset vector. And that's it. Now for the Z80, the interrupt service routine is always in address 66. There is no interrupt vector. The Z8 will always go to 66 for the non-maskable interrupt service routine, and what it will find there is just a return as well. In the case of the Z8, it takes 2 bytes, but it's just return from interrupt, just like for the 6502. The Z80 always fetches the first instruction at address 0000. So to maintain consistency, we want the Z80 to actually start at 202. So what do we put at that address 000? We put a jump to 202. And that's where the code will start. And this takes 3 bytes. Now, at the end, we change the flag to inform the BIOS that, okay, now the CPU is running. And then we reset the CPU. We'll pull the reset high. We pull CPU go high, which will take the CPU out of a halt high impedance state. It will allow the CPU to control the buses again. Then it waits 5 microseconds just for safety, and it will pull the reset line low. And from this point on, the CPU can just go and execute whatever program it will find at address 202. Now this is the directory function. It just uses the built-in SD library of the Arduino IDE. I'm not going to go through the details of this. It's just standard stuff to list the files that are in the micro SD card. Delete file, also very standard stuff. It just calls a function called SD remove and the file name. Save, also very standard stuff. Most of it is to check that the user has entered all the arguments that are needed and that the arguments don't violate any of the conditions. And then it just writes data to the file and closes the file. So pretty standard stuff as well. The same thing for load. And then here you start getting the low-level functions of the BIOS, the functions that are used by the system itself. The Jingo, what it does to clear screen, which is just printing spaces everywhere. The Cerberus clear screen printed spaces literally everywhere. These ones, the CLS, only print spaces within the wireframe. And this is to print the wireframe. This is to just print a string on the screen, to print a character on the screen. And these functions use this cpoke. cprint string uses cprint char, and cprint char uses cpoke. So at the end, everything is a cpoke or a cpeak. Test memory is just a loop that pokes and peeks from every memory, all the character set multiple times. This is just an internal address translate function, so we print things within the wireframe, so we don't print things that overlap with the wireframe. This is the procedure to reset the CPUs. It just pulls the reset line and CPU select and CPU go in the right order. That's all there is to it. These are the shift register functions to allow CAT to communicate to what is essentially a parallel bus architecture, while CAT is just a serial controller. And these are the core functions of the system, cpoke and cpeak, that just use digital writes and the shift register in spacer to allow CAT to communicate to the memories and the CPUs. And that's the end of it. In fact, that's quite literally the end of it. The project is done. I have done all the stress testing I wanted to do. I have milked all the fine-tuning I think I can milk out of all these tests. I think if I bring any other change into Cerberus right now, I probably would just make it worse. I'm not going to risk trying to put a assembly language monitor in the space I have left on the embedded flash memory of CAT. Although I have more dynamic memory now, it's less than 1 kilobyte of dynamic memory, and now the instruction memory is getting close to 80%. So it's a futile enterprise to try to put an assembly code monitor in CAT. The assembly or the assembler will have to run in one of the CPUs as a normal Cerberus application, but that is coming. The only thing I still need to do is to make a couple of small corrections to the PCB and order a new batch of PCBs. I don't want my Cerberus to have that bodge, that ugly bodge you saw. And I'm going to send a couple of assembled units to people who are willing to or maybe willing to write software for Cerberus. And that will be it. So there will be one more episode, but basically an aesthetic episode, not a content episode. I will just show you the alterations to the PCB design. I will probably show you the final board fully assembled with the nice clean plexiglass trays around it. And just celebrate the completion of this project. It has been for me 7 months now, working on this on some evenings and most weekends. It's been a great project. It has been a lot of fun. Put me in contact with the kid that still lives in me, and I'm looking forward to the next project already, but I will document Cerberus fully over the next couple of weeks before I put it all up on GitHub. So don't you worry about it, there will be full documentation. Yet content-wise, we've reached the end of the road, a very, very satisfying end of the road for me, at least. I hope you've enjoyed. I hope you've taken something out of this. You've learned something or had some insight. Not that I have much to share, but what I have hopefully has been useful to you. So thanks for being on this journey with me all this time. I hope you are safe and well in these crazy times we're living in the world and having fun safely at home with our beloved retro technology. Take care, and I will see you one more time for the final episode of the Cerberus saga.